Welcome to Study Loop.
Hello everyone, today we're doing chapter 14, problem 4, and this problem asks us how many unique proton NMR signals would each of these dimethylcyclopropane molecules show. So remember that your proton NMR will identify a unique signal as being one of the protons that is chemically distinct and in a unique microenvironment than the other protons on a molecule. So let's see what I mean by that. So in order to identify how many chemically distinct, unique protons we have in a unique microenvironment on each molecule, let's first identify all the protons. Well, using stick notation, we know that these methyl groups each have 3 protons. And here we have 2 protons, one going up, one going down. And same thing on this carbon. So in order to determine how many unique chemically distinct protons we have, we need to determine if there's an internal plane of symmetry on our molecule. So if we identify, yes, this molecule actually has an internal plane of symmetry, cutting right down its middle like this. So that means that we know that these protons on this side are going to be the exact same as these protons on this side. So for example, this proton here is exactly identical to this proton here. They exist in the same chemical environment. These carbons are both bounded to 2 carbons, this upper carbon being bounded to 2 more carbons. So same thing on the left side as the right. And same thing for all of these carbons and protons here. So we know that we have an internal plane of symmetry, so what we see on one side is going to be the same as what we see on the other side. So that kind of helps us down to identify unique chemically distinct protons. So we can clearly tell that these 2 protons on this carbon are distinct from these 3 protons on the methyl group. We see that these 2 carbons exist on a cyclical carbon atom that's bound to 2 more carbons, while these protons here are bound to a terminal methyl group, which is bound to 1 more carbon. So the electronic microenvironments and the electron density distribution are different for these 2 sets of protons. So and actually let me just draw the top one in a different color so we can really visualize them being unique. So if you guys remember, what is true on this side is also going to be true on the other side. So these 3 protons are identical to the left side, while these 2 protons are identical also to the right side. So as you see here, we have 2 unique chemically distinct protons here. So now let's do this in problem B. So problem B, we also identify that we have an internal plane of symmetry, but now our methyl groups have some sort of stereochemistry associated with them. So because we have stereochemistry, we know that in order to satisfy all the bonding, there must be a proton that goes down within the page on both of these carbons. And we know that there'd be a proton here as well as a proton here. And we know that these methyl groups also have 3 protons. So now we know that in this case, we have to consider the stereochemistry of this molecule because these 2 methyl groups are facing up. So if I were to redraw this structure, something that looks like this. So I'm drawing this flat now. We see that these 2 methyl groups are going up like this, and then that means the protons are going down. And there's a proton here going up. Let me draw that better. On this carbon, there's a proton going up, and there's also a proton going down. And then here, there'll be 3 protons on each of these carbon methyl groups here. So now what we see is that this proton here, that's on this carbon here, is cis to these methyl groups. So it's on the same side as these methyl groups. But this proton down here is trans to these methyl groups. So although we have an internal plane of symmetry here, and these two protons are bound to the same carbon, even though they are bound to the same carbon, as you see here depicted by the internal plane of symmetry, these two protons will be different from one another. Why? Well, because once again, the top proton is cis, to these two methyl groups, while the bottom proton is trans. So clearly, these are two unique microenvironments, so therefore they're two unique distinct protons. But what we know is that these three protons on a methyl group and these three exist in the same microenvironment. So these 6 protons are all identical, and then also the converse is the same is true for these bottom 2 protons. So these 2 protons are also the same. So in total we have 1 type, 2 type, 3, 4 unique chemically distinct protons. Therefore we'll have 4 different NMR signals. And now if we look at this bottom example, and once again if we redraw it such that it's really clear to us regarding the stereochemistry of this molecule, we know that 1 carbon is going up while 1 is going down. And also, once again, we know that these methyl groups represent 3 protons coming out of them, out of the carbon. Same with the bottom one here. And we know that if there's a carbon going down here, that means we have a proton coming up. And if there's a carbon going up, that means we have a proton going down. And on this upper carbon, we have 1 proton up, 1 proton down. So if we look, once again, starting with this central one, we see that this proton is cis to this methyl group, but is trans to the bottom methyl group. And the same is true for this bottom proton. This bottom proton is trans to this methyl group, but it is cis to this methyl group. So we know right away that these 2 protons are, so if you look at it, actually, we see that the top proton is cis to this methyl group, trans to this methyl group, while the bottom proton is cis to this methyl group, trans to this methyl group. So these protons, even though the left and right side differ, the total summation of their microenvironments are the same, because the upper proton is cis to a methyl group, trans to a methyl group, and the bottom proton is cis to a methyl group and trans to a methyl group as well. So these 2 protons, in essence, will be considered the same, as they exist in similar microenvironments to one another. Not only that, we see that the 3 protons up here on each methyl group, we see that these 3 protons up here on these methyl groups, these protons are cis to 1 proton and cis to 1 proton here, while the bottom methyl group is also cis on this proton and cis to this proton. So the interaction and the proximity to other nuclei that share the same identity are also the same for both of these methyl groups, even though they're on opposite sides of the molecule. So these 2 sets of 3 protons are also going to be the same. And this leaves us with the last set being these 2 other protons, which are on the opposite side of these methyl groups, and they also exist in the same chemical environment. So if we see here, we have 3 unique, distinct chemically distinct protons that exist in unique microenvironments. Therefore, we'll get 3 distinct NMR sequences and signals.